for every D from the first pi system, for every F from the second pi system, and we would like to show the same result holds for every D from the sigma algebra generated by the first pi system and for every F from the sigma algebra generated by the second pi system. So hopefully this is something that is familiar to you. Anyway, so let's prove it. Let's prove it. The idea is that we have a difficult proof because we have to change two pi systems to sigma algebras. We have to do it one by one. Let's do it one by one. Okay? Let's first fix. Let's add an intermediate step and show this result for every D in the sigma algebra, but F from the pi system. Okay? So to make things easier, let's continue in two steps. Step one is to show D cross F is in sigma P for every D in E, but F in pi 2, pi system number 2. And to do this, let's fix this set from the pi system and define the collection of sets for which this is true. Well, just okay. D cross F is in sigma P. Okay. So, what do we need to do? What do we need to do? What do we know about this D1? What do we know about D1? What can we say about D1? D1 contains which collection? Yes. P1. D1 contains P1 because we have D cross F in sigma P for every D in P1, and F is fixed from P2. So we know P1 is a subset of D1. Show D1 is a Dynkin system on E. Then this is left as an exercise by monotone class theorem. We are done. Sigma P1, which is script E, is a subset of D1. So D cross F is in sigma P for every D in E and F in P2. Just read what it means to have script E is a subset of D1. This is precisely this statement. Okay? So this is step one. Step two is to extend it to the case where D is from the sigma algebra and F is from the sigma algebra, which is the full result. So step two, show D cross F is in sigma P for every D in E and F in script G now. So now we're going to fix the first set, fix D in E, and define D2, which is the collection of sets F such that D cross F is in sigma P. Now what can we say about D2? What can we say about D2? Does it contain P2? Does it contain P2? Yes, why? How? From step one, exactly. So if we didn't do this step one, we couldn't have said that P2 is a subcollection of D2. This is by step 1. Because look at what step 1 gave us. For every D in E, and for every F in P2, F from P2. The rest is routine. Show D2 is a pi system, a Dynkin system, is a Dynkin system on G. Then by monotone class theorem, sigma P2, which is script G, is a subcollection of D2. So we are done. We are done because G is a subcollection of D2. Just means that we have D cross F in sigma P for every D in E and F in G. We just didn't check that P is a pi system. I leave it as an exercise, okay? That is the easier part. This part was difficult, so we showed it using 2 monotone class arguments. Okay? Even one is not enough, so we have to use 2. I wanted to do this proof here because it is pretty much the same as one of the midterm questions. The story was different. It was about independence, but again, you need to show, you need to pass from here to here. You have a property that holds for sets coming from pi systems, 2 pi systems, and you need to show the same property for sets coming from their sigma algebras, corresponding generated sigma algebras. Okay? And you do it one by one. Okay? If you have n spaces, you need to do it n times. Okay? That's why we deal with 2 spaces first. So since we're at it, I'd like to say a few things about this pi system, about this product sigma algebra. So using tracing, we can also talk about the sigma algebra on a subset A of E cross G. Well, for instance, let's say you have E equals G equals R, and you have the Borel sigma algebra on R2 now. It is the product sigma algebra. Okay? And let's say you have a set, which is just R2, right? A subset of R2. So I'm not interested in the full space, but I'm just interested in maybe a box, or even something uglier, just some subset of R2. If I'd like to live in the smaller world, if this is my new world, I'd like to look at the sigma algebra on the smaller world. And I can do it because I know tracing, right? Give me a sigma algebra on a big space, do tracing to get a sigma algebra on the smaller space, right? So the Borel sigma algebra on A is nothing but the collection of sets that are intersections of this smaller world with the Borel subsets of R2. So you can talk about the Borel sigma algebra on 0, 1 cross 0, 1. You can talk about the Borel sigma algebra on a finite set cross finite set. Well, this is going to give you the power set. Just check it. So the trace of the Borel sigma algebra on a countable subset gives the discrete sigma algebra as a note. So that was the case in the one-dimensional structure. Whenever you have a random variable taking just finitely many values or countably many values, there is potentially some ambiguity about the choice of the sigma algebra, because on one hand you can look at the trace of the sigma algebra on the real line on that finite or countable set, or you can, since you have just a finite or countable set, you can just choose to work with the discrete sigma algebra. And the conclusion was that there is no ambiguity. Indeed, the trace gives you the power set. And the same happens in the two-dimensional and even multi-dimensional case. So there is no ambiguity. So now we have some sigma algebra on the product space. Well, we can do two things with that. First of all, we can look at a function defined on the Cartesian product, on the product space, or we can look at a function that maps into this product space. Okay? So either your E cross F, so E cross F, no, G, right? E cross G, this world, E cross G, you either map from here to some other place, or you can have an abstract probability space on which you have a random variable taking values in E cross G. So let's look at this first, okay? And then we're going to look at the second case. So first we're going to use E cross G as a domain, okay? So measurability of a function on E cross G. Measurability of a function on E cross G. Okay, so for this, let's fix another measurable space as the image space. Let H script H be another measurable space. So now that we have E cross G as a sigma algebra on E cross G, we can talk about the measurability of a function. F defined on E cross G, mapping into H. Let's say H is here, okay? Let's say H is here. So you have a point xy, which maps you to f of xy, a point in H space. The definition of measurability is something you know very well now, right? You just take a measurable subset of the image space and look at the pre-image. The pre-image of K with respect to F. So this measurability is simply F inverse K, which is the set of xy's, for which f of xy is in K, must be measurable with respect to the product sigma algebra for every K in the sigma algebra of H. I just rewrote the definition of measurability for the special case where the domain is a product set, product space. But this is not a new definition. This is just applying the old definition. Okay? So you can see this f as a multivariate function, right? But there is nothing different in terms of the definition of measurability. because you have a sigma algebra on the product space. So you can just treat it as an ordinary measurable space. You can just treat E cross G as an ordinary measurable space. What is interesting in this situation is to look at sections of a function. You know, whenever you have a function of x and y, you can freeze x and look at this function as a function of y, or you can freeze y and look at it as a function of x, right? You can see it as a function of one variable if you fix the value of the other variable. So hopefully, this operation preserves measurability, right? So you have a measurable function defined on the product space. Hopefully, its sections, namely the one variable versions of this function, are also measurable. Okay? So what do I mean by sections of f? Sections of f. So you either fix x0 in E, and then you can define the section of f at x0 as a function of y, which is defined as f of xy, x0y. So this f x equals x0 function is on the second space from the eighth space, the image space. So you do it for every y in G. Or you can fix y0 in the second space and define f, the section of f at y equals y0 as a function of x, as a function of the first variable, which is defined as xy0. And this is a function from the first space into the h space, the image space. Just take h to be the real line, and things are nice. So the proposition is that if f is measurable, then fx equals x0, fy equals y0 are also measurable for every fixed x0 or fixed y0. Okay, so what is this function doing? What is this function doing? Well, let's fix an x0, okay? Let's show fx equals x0 is measurable for fixed x0. So what is this function doing? Its input is y, and its output is f of x0y. Okay? So let's try to pass from y to f of x0y in two steps, okay? You have your y. You can add an x0 in front of it and make it a pair. Let's add a middle step, an intermediate step. Okay? And then, so this is the first step. The second space is just to apply f. Just apply f. And what is this first step? Well, let's give it a name. Let's call it h of x equals x0. Okay? So this is in space G, mapping into E cross G, and f is mapping into h. So we can write f x equals x0 as the composition of f with h of x equals x0. Composition of two functions. Now, why did I do that? What do I know about preservation of measurability? So how can we conclude that fx equals x0 is measurable, given this representation as a composition? Do you remember anything about the relationship between measurability and composition of functions? Yeah, what do you know? So if this is measurable and this is measurable, what can you say? Composition is also measurable. So compositions preserve measurability, right? So if you have composition of two measurable functions, it is measurable. So we are given that this is measurable. All we have to do is to show that this is measurable. Show this is measurable. And then, at the end of the day, we're going to have that this is also measurable. Measurable as a composition. So let's check that this H is measurable. Let's show H x equals x0, which is defined on G, mapping into E cross G, is measurable. Okay? In other words, show H pre-image of a set in the measurable with respect to the product sigma algebra is in script G for every A in the product sigma algebra. This is the pure definition of measurability. But of course, this is difficult to check. Okay? This is difficult to check because you need to check it for every A in the product sigma algebra. What is enough to show is that you can just check that this is true for sets A that are measurable rectangles, because measurable rectangles form a collection generating the product sigma algebra. Just look at one of the very first lemmas in measurability of functions. You will see that whenever you have a collection, not necessarily even a pi system, on the image space, it suffices to check measurability for sets coming from this collection generating the product sigma algebra, the sigma algebra on the image space. So enough by a lemma in section 2.1 that H x equals x0 of D cross F is measurable for every D in E and F in G, because these are measurable rectangles. So let's do it. Hopefully now it's easier. Let D in E and F in G. So we look at the preimage of this function, of this set under H. So what is the definition of it? Just a set of y's. Remember, H is defined on this space. So a set of y's for which H of y is in D cross F. Set of y's for which H of y is in D cross F. But what is H of y? What is H of y? Well, H of y is just x0y. So x0y is in D cross F. This simply means that x0 must be in D and y must be in F. But your x0 is fixed. So if x0 is not in D, you just have empty set. No y can satisfy this property. But if x0 is in D, then you're fine. This condition is already satisfied. Therefore, your preimage is just F, because all points in F satisfy this property. So you have just F. Let me write if. Since x0 is fixed, it is really binary. You have it or not. And this is always measurable. So is in script G, right? Because F is in script G, empty set is always in script G, so this is measurable. So we're done. H x0 is measurable. So f x0, which is the composition of H with, no, the other way around, F with H is measurable. Fy equals y0 is similar. Just symmetric proof. Change the roles of x and y, and this follows. So these are just simple properties that make our life easier when dealing with multivariate functions, right? You can fix one variable and look at it as a function of the other variable, and it should preserve measurability. So we had to check this. And you can do the same operation to sets. Okay, you can also look at sections of sets in the product space. Okay, it is very easy to describe on a picture. So if you have, let's say, sections of a set A, you have, let's say, E and G, and you have just a set A, okay? So the section at x equals x0 is nothing but this set, right? Fix the variable, first variable, look at it as a subset of the second space. Fix the second variable and look at it as a subset of the first space. So you can see this line segment as a subset of the first space, and you can see this one as a subset of the second space. So let's define, so fix x equals x0, and then you can define as the set of y's for which x0y is in A, and fix y equals y0, then you can define the section of A at y equals y0 as a set of x values for which x and y0 is a point in A. So x0 and y is a point in A, but you see it as a subset of the second space, or in the second case, you see it as a subset of the first space. So the corollary to our proposition about sections of functions, or as a subset of the first space, so I have to write script E for every fixed x0 in first space or y0 in the second space. So, well, the proof will be an application of the proposition. So how can you pass to the setting of functions if you are in the setting of sets? What is the tool to pass from sets to functions? Indicators. So let's look at the indicator of A, indicator of x equals x0, indicator of y equals y0. This means our function will just be a numerical one, right? We will just fix the third space as the real line, okay? So I'm just going to sketch the proof. Let's just take H equals R and F equals indicator A. Then the section of the indicator function is going to give you the indicator of the section of X. And section of the indicator function at y equals y0 is going to be the indicator of the section of the set. And we know that an indicator function is measurable if and only if its set is measurable. Therefore, by proposition, this is a measurable function which just means that the set here is measurable. So follows directly by the proposition. I leave the details to you. Okay. So again, this is an earlier lemma we proved at some point. The indicator function of a set is a measurable function if and only if that set is a measurable set. Okay. And this observation is just an observation. Just check it yourself, right? The section of the indicator function is the indicator function of the section of the set. That is an observation. I would also like to add an exercise. So here we looked at the function h, which maps y to a pair where the first coordinate is fixed. Okay? You can do the opposite. You can do the opposite. Given a pair xy, you can just look at its first coordinate or the second coordinate. These are called coordinate mappings or coordinate functions. Okay? So an exercise is that let us define the coordinate 1 or coordinate 1 function, yeah, from E cross G to E by C1 of xy is just x for every xy in E cross G. And also define C2. So just delete the second one or just delete the first one by C2 is the second one. C1, C2 are called the coordinate mappings. And they are measurable. And they are measurable. So these are functions that come for free. You don't need to have a function that is defined by somebody else, like an f. This is a very natural function. Whenever you deal with a product space, of course you would like to deal with coordinates of this point on the product space, right? So this function, which gives you each coordinate, must be measurable. Okay? So this is the very natural function that you can define on a product space. Okay? It has nothing to do with randomness or some functions that you define on your random experiment. This just comes for free. Whenever you have a product space setting, you have coordinate mappings automatically, right? They come for free as part of your framework. So these are measurable functions. And that is the claim of this exercise. Okay. So this is pretty much what I'd like to say about product spaces. But we did it for 2 spaces, just for fun and just as a reiteration of the ideas. I'd like to state these things in multiple space case. Okay? The product of finitely many spaces. Just to fix some notation and so on. Okay? Okay. Product of finitely many measurable spaces. So unfortunately, I cannot use E, G, etc., etc. So now we have to number them. So E1, script E1, etc., En, script En, measurable spaces. So the product space is product measurable space is the Cartesian product of the spaces and the product of the sigma algebras, denoted this way. Or you can write it as in the longer way, right? So this is just Cartesian product. I don't need to define it, right? Product. And this is the sigma algebra generated by measurable rectangles. Now they are n-dimensional, so di is coming from ei for every I. And in this setting, it is still true that you can have pi systems generating individual sigma algebras, can create a pi system generating the product sigma algebra. I'm talking about the proposition that we proved using two monotone class arguments. Let's say you have a pi system on the first space, pi system on the second space, pi system on the nth space, and you look at products of the form, products of sets, measurable rectangles coming from the individual pi systems. Then this collection generates the whole product sigma algebra. I mean, you can write the n-dimensional version of this proposition. Okay? Those propositions like measurability of sections of functions, measurability of sections of functions or sets, measurability of coordinate mappings, they're all valid. They're all valid. I don't need to say anything. So if you have n-dimensional space, you have the first coordinate mapping, second coordinate mapping, nth coordinate mapping. That is just an extension. And of course, you can have a Borel sigma algebra on Rn, which is generated by rectangles of the form minus infinity to b, 1 to minus infinity to b, n, where b1 to bn are reals. That's the Borel sigma algebra on Rn. Etc., etc. So you can do tracing. You can also talk about Borel sigma algebra on a hypercube, right? Via tracing, etc., etc. Okay, so back to this picture. Maybe first of all, any questions? Any questions? Yes?
Can you propose exactly the same things by just letting n go to infinity and say countable many measurable spaces?
No, one has to be careful. One has to be careful. We're going to define, you can define products, product sigma algebras, on the product of infinitely many spaces. And it can even be uncountably many spaces. This can be done, but one has to be more careful. So it is not like a trivial extension. Okay? There are technicalities and so on, but this generalization to n-dimensional spaces is more or less trivial, let's say by an induction argument. Okay? But the infinite case, it is more involved. Any other questions? So we had this picture, right? We had this picture. You can use this product space as a domain of a function. We did this. We did this. You can use this as the image space of a random variable. And this is what we're going to call random vector. Okay? So now random vectors. So let omega f be a measurable space. And consider a function x from omega to the product of those n spaces. I'm going to use the setting in this previous subsection where you have n measurable spaces. Okay? We are really at this stage, at this part of the picture. Okay? Omega to product space. So we can talk about its measurability, right? So just a proposition, x is measurable with respect to f and the product sigma algebra. Well, whenever you have an x, you can talk about its coordinates, right? I forgot to say this. Coordinates. This xi of omega is, well, xi is just the ith coordinate of x. The result is that x as a function mapping into the product space is measurable if and only if all of its coordinates are measurable. So you don't need to worry too much about measurability of a random vector. If the components, if the coordinates are measurable, then it's fine. So xi is measurable with respect to f and script ei for every I. Okay. Let me leave it as an exercise. It's not very difficult. Well, let me not write, but just say in words that the ith component is just the composition of the ith coordinate mapping with x. We argued that the coordinate mappings are measurable. I left it as an exercise, I guess. So if this is measurable and this is measurable, then their composition is measurable. So one way is trivial, right? If x is measurable, then xi is measurable because it's the composition of two measurable functions. So we don't have to worry too much. And whenever x is measurable, we say x is a random vector. Random vector. So now, what is the distribution of random vector? What is the distribution of a random vector? For this, we need to have a probability here. Suppose we have a probability measure P on omega f. Then is the distribution. So probability composition with pre-image mapping is the distribution of x under P. Well, what do I mean by that? Well, we just look at the probability that x takes values in some set D, right? In some set D as a function of D. So D is coming from the product sigma algebra. And this is a number between 0 and 1. So this is what the distribution does. And sometimes we say, so this is sometimes called the joint distribution of x1 to xn. It is simply the distribution of x, but we sometimes say it is the joint distribution of the components of x, the coordinates of x. I'll say one more thing, and then we'll go. So this one more thing is that note that this product sigma algebra is generated by the collection of all measurable rectangles, which is a pi system. So remember the uniqueness result, uniqueness of measures, uniqueness of probability distributions. So if you have two probability measures that agree on a pi system, then they must agree on the full sigma algebra. So if you look at the values of the distribution at measurable rectangles, so probabilities of this form, they characterize the whole distribution. So it is enough to just look at probabilities of the form x1 is in D1 and xn is in Dn. Note that this is not as general as this kind of a probability where D can be a non-rectangular set. But it is enough to focus on rectangles. First coordinate is in some set, nth coordinate is in some set. Okay? So the values of this for all D1 in E1 and Dn in En uniquely determine the distribution of x, which is the joint distribution of components. So you don't have to worry too much about looking at very ugly sets in the product space, because the distribution of your random vector is entirely characterized by probabilities of this form. This coordinate takes values in this set. This coordinate takes values in this set. Joint probabilities, right? Joint probabilities. So next time, we're going to look at the relationship between these kinds of probabilities and marginal probabilities. Probability that x1 is in D1, full stop. Probability that xn is in Dn, full stop. Just that kind of marginal events, okay? So for today, we're done. Thank you.